So hey guys, welcome to my channel. I am Santosh and here in my channel I discuss topics from physics and mathematics. As usual, today I am here with one more new video for you guys, and in this video I am going to discuss one of the very important topics from electrostatics, and that is Coulomb's law. But before this, let us quickly look at some of the basics that we need to know to study this topic. Let us start with the very basic thing, that is charge. Charge is an intrinsic property of matter, and it is this property because of which objects experience electric force, and all the charge in the universe is due to protons and electrons. Charge is available in two types, that is charge on proton is different from charge on electron. By convention we take charge on proton as positive and charge on electron as negative. But the magnitude of charge on proton is equal to the magnitude of charge on electron, which is equal to 1.6 into 10 raised to minus 19 coulomb. Next, regarding the interaction between charged bodies, we have like charges repel each other and unlike charges attract each other, which means if you bring two positively charged objects close to one another, they repel each other. Same is the case with two negatively charged bodies. But if you bring one positive charge and one negative charge close to one another, they attract each other. Finally, if the body has equal amount of positive and negative charges, it behaves as if it has no charge, and we call that body as neutral body. So neutral body does not experience electric force. Guys, with this information, we can easily tell what happens when we bring two charged bodies close to one another. But what we cannot tell is the magnitude of the force or the strength of the force. Now the question is, can we tell the magnitude of the force if we know the charge on two bodies and the distance between them? The answer is yes, and it was given by French physicist Charles Augustin de Coulomb in 1785. And that is our Coulomb's law. Guys, Coulomb's law quantifies the interaction between charged bodies. It gives us the formula to calculate the magnitude of force between two charged bodies. But before going to the formula, let us first look at the statement of the Coulomb's law. According to Coulomb, the magnitude of the electrostatic force of attraction or repulsion between 2 point charges is directly proportional to product of magnitude of their charges and inversely proportional to square of distance between them. And these forces always act along the line joining the centers of two charged bodies. Guys, now let us understand the meaning of this statement by decoding some important relations. But before that, if you read this statement carefully, the Coulomb's law is talking about the force between 2 point charges. If you don't know what point charges are, listen to me now. If the sizes of the charged bodies are much smaller than the distance between them, then the physical sizes of these charged bodies are ignored, and the charge on these bodies can be assumed to be concentrated at single point. So these kind of charges are known as point charges, and this assumption is very important. So whenever you apply Coulomb's law, you always need to make sure that charges involved are point charges or not. Now coming back to this statement, it says that the force between 2 point charges is directly proportional to the product of magnitude of these charges. What does that mean? To understand that, let us consider 2 point charges Q1 and Q2 separated by some distance r. Now Q1 will exert force on Q2 and Q2 will exert force on Q1. The force on Q1 due to Q2 is denoted by F12 and force on Q2 due to Q1 is denoted by F21. By Newton's third law, we know that forces always exist in pair. So F12 and F21 are action-reaction pairs. They are equal in magnitude but opposite in direction. So we can write the magnitude of F12 is equal to magnitude of F21 is equal to some F. Now the relation says this magnitude F is directly proportional to the product of magnitude of two charges, which means if you increase the magnitude of one charge or the both of the charges, the force will also increase. The magnitude of force will also increase. In simple words, more the charge, more is the force. So mathematically, if I write the magnitude of F is directly proportional to mod of Q1 into mod of Q2. This can also be written as mod of Q1 Q2. Now if you look at the next relation, the Coulomb's law says that the force between 2 point charges is inversely proportional to square of distance between them, which means if you increase the distance between 2 point charges, the force between them will reduce. To be precise, if you increase the distance by 2 times, the force will reduce by 4 times. Now if I write this relation mathematically, I have mod F is directly proportional to 1 by r square. Here r is the distance between 2 point charges. Now combining these two relations, I can write that mod F is directly proportional to mod of q1 q2 divided by r square. So the magnitude of force is proportional to this ratio. Now to turn this relation into an equation, we need to introduce a constant of proportionality. We need to introduce a proportionality constant. So finally we have the magnitude of force F is equal to k mod of q1 q2 divided by r square. Here k is the constant of proportionality and this is known as the Coulomb's constant. The Coulomb's constant k is also expressed as 1 by 4 pi epsilon. Here epsilon is the permittivity of a medium in which the two charges are placed. This is the property of medium and the value of epsilon changes from medium to medium. So the value of k also changes from medium to medium. So we'll talk more about this k in our next video. So finally we have this formula, that is F, the modulus of F is equal to k mod of q1 q2 divided by r square, which gives us the force between 2 point charges which are placed at distance r. Now the question is, how did Coulomb arrive at this relation? To understand that, we need to look at the experimental setup and the procedure used by the Coulomb. Guys, Coulomb used the torsion balance to measure the force between 2 point charges. The torsion balance is a sensitive device and as you can see from your screen, it is made up of several parts. The torsion balance has a cylindrical glass case which isolates the experiment from the outer environment. And through the top of that glass case, we have a tube that is attached to it, and the top end of that tube is covered by a lid, and we call that lid as a torsion head. Connected to the torsion head, we have thread that is hanging inside the tube, and we call that thread as a torsion fiber. If you see the diagram, the lower end of the torsion fiber is connected to a needle that is hanging inside the glass case, and one end of the needle is connected to a small metal disc or a metal sphere. We also have a metal rod that is hanging inside the glass case, and both of the ends of the metal rod are connected to two small spheres. And if you see the diagram, we have one sphere inside the glass case and one sphere outside the glass case. And finally we have a scale that is attached to outer surface of the glass case to measure the force between two small spheres. Guys, now let us focus only on the spheres which are inside the glass case. Here we have two spheres, one that is attached to the metal rod and the other which is attached to the needle. And if you observe here, the sphere that is attached to the metal rod is stationary. It cannot be moved. On the other hand, the sphere that is attached to the needle can be moved easily inside the glass case. Now imagine a situation when the charges on both of these spheres is 0. That is, when both of these spheres are neutral. In that case, we can move the needle such that we can bring them closer to one another, or we can even touch them both. So what Coulomb did was he gave both of these spheres the same type of charge, either positive or negative. So due to force of repulsion, both of these spheres got separated, or due to force of repulsion, they moved away from each other. The sphere that is attached to the metal rod is stationary, so it didn't move anywhere. But the sphere that is attached to the needle moved away from the other sphere. So when it moved away from the other sphere, the torsion fiber got twisted, right? The thread got twisted inside the tube, and that twist was the measure of the amount of force. If force is more, then there will be more twist. So Coulomb measured the twist using the scale that is attached on the outer surface of the glass case. Guys, what Coulomb observed was when he increased the charge on the spheres, the twist in the fiber was also increasing, which means the force is directly proportional to the charges on the spheres. And also what he observed was when he increased the distance between two spheres, the twist in the fiber was reducing, which means the force is inversely proportional to the distance between the spheres. So later he conducted the experiment with different magnitudes of charge and separating them by different distances, and he came to conclusion that force is directly proportional to the charges and force is inversely proportional to the square of distance between the charges. And he finally formulated this formula which gives us the magnitude of force between 2 point charges. But one challenge Coulomb had was during his time, there was no means of measuring the charge on the body. So how did he come to these conclusions then? For this, he used a simple and a brilliant idea, where he took a charged metal sphere and assumed that charge on that sphere is Q. And he took another uncharged identical sphere and brought these two in contact with each other. Now, due to symmetry, both of these will receive equal charges. So each sphere will have Q by 2 and Q by 2. Now he took this Q by 2 and again brought another uncharged identical sphere. And again he brought them in contact with each other and then produced the charge of magnitude Q by 4 and Q by 4. Now he continued this process and obtained the charges Q by 8, Q by 16 like that. Now using these different magnitudes of the charge, he conducted the experiments and came to the final conclusions. Guys, although the Coulomb's law helps us in finding the magnitude of force between 2-point charges, it also has certain limitations. So now in the final part of this video, we'll see where we can and where we cannot apply this Coulomb's law. Case number 1. Coulomb's law is only applicable for point charges. Guys, if the sizes of these charged bodies are larger, then we cannot apply this law. Especially if the shape of the charged body is irregular, then the inverse square relation between distance does not hold true. So in that case, we cannot apply the Coulomb's law. The Coulomb's law is only restricted to point charges. Case number 2. The Coulomb's law cannot be applied to moving charges. If the charges are moving with respect to one another, then we cannot apply the Coulomb's law. The reason is, when a charge moves, along with electric effect, it also produces magnetic effect. So along with electric force, there will also be a magnetic force. So the Coulomb's law alone will not be helpful for finding the force between two moving charges. So in the case of moving charges, the Coulomb's law cannot be applied. So Coulomb's law is restricted to static charges or the charges at rest. Guys, with this we come to the end of this video. If you like the video, please hit the like button and share this video with your friends. And also don't forget to subscribe to my channel. Guys, before signing off, I will give you an exercise problem to solve and write down your answer in the comment section below. So guys, thanks for watching and stay tuned for the next video.